a zoom button, and that's all I really need. Okay. So now we are moving on to chapter, I don't even know my chapter numbers. What is happening today? 11, chapter 11. So I'm going to put this on the screen. Let's zoom a little bit. Can I zoom? I want to zoom. Allow me to zoom. It doesn't. Oh, there's the plus. All right. So the first thing, before we worry about factors and multiples, is that this prime factorization property of all integers. We saw that previously there's a main result when it comes to prime numbers that we can factor any integer into some prime numbers, a product of prime numbers being multiplied together to give me my number. So in that sense, then, the prime numbers are the building blocks of all integers, because you give me any random integer, either it is a prime number itself or it's made up of prime numbers being multiplied together. And for any specific integer, there's only one way. Maybe you can shuffle the prime numbers around, but it's still the same collection of prime numbers making that number. So let's look at exercise 11.1. Now, if the number, actually, yeah, the number can be big too. It just takes me longer, of course, to find those prime numbers. So we'll pick something maybe in the hundreds and thousands, nothing too crazy. A nice way to visually as well find which prime numbers make up 100, for example. So I want to know what prime numbers are multiplied together to make 100, because itself is not prime, of course, 10 squared and so on. I can do that by way of a factor tree and say, I'm just going to split my original number up into two numbers multiplied together, and the obvious one is maybe 10 times 10, right? Now for each of these, this 10 is not a prime number, which means it can be split up, and I'm just going to go 2 at a time, 2 and 5. Now 2 is a prime number, and 5 is a prime number, and that ends those paths. Then I'll go to the other number that is at an end, which isn't the prime number yet. This happens to be a 10 again, and I can split that into 2 times 5. And I stop when all my branches end in prime number. And I'll put circles around them so I can easily see them. So that then means that 100 can be written, and the order doesn't matter, but I go in increasing order as 2 times 2 times 5 times 5. Now you can shuffle those around, but still 100 is made up out of 2 2's and 2 5's, regardless of how I write them. Those are the building blocks of this number. You can write them like that, or you can use exponents, which is the representation for repeated multiplication. And I can write 2 squared times, sometimes a dot, if you don't like the time symbol, 5 squared. Either one of them, they're all the same, right? Regardless of how you write them, 100 is made up out of 2 2's and 2 5's. So the factor tree is something that is in the curriculum as well. Oh, don't ask me the grade. These things change depending on the skill of the class. But later grade, maybe a 5, once they have multiplication down, prime numbers, factor trees, and so on. So it's very useful to me to circle the prime numbers, circle the ends of these branches, so I can quickly see everything I need to list. Okay, so that's one of them. There's no need to make a number too big. Let's do another one, and it is 294. And we'll use these in the upcoming examples. So 294, what prime numbers make that up? So the factor tree is convenient in the sense that I just worry about splitting it up into two numbers at a time. And it doesn't really matter which two you want to use. So I don't waste a lot of time looking for the two numbers to be similar size or anything, just whatever you see. And if all I see is, well, this number is even, so it's going to be 2 times something. If that's all I see, that's fine. Don't spend a lot of time um, trying to come up with bigger numbers or anything. It doesn't matter. Any split uh, of the number into the product of two numbers is fine. So then, maybe to be sure, I'll do a little division. 294 divided by 2 to get the other side of that split. And I get that it is, oopsie, 147. So now 2 is a prime number. So in this case, my one branch finishes very quickly. Now I have to decide, is 147 prime number as well? Now, in some rare cases, I have to do the full prime number test if by making my list and making sure my list is complete and so on. But I just check my divisibility tests, and usually one of those will catch it. And if none of them do, then yes, I have to make sure. But in this case, I see the sum of the digits, they add up to 12. So this is divisible by 3. And then I just have to find the other number. I can be sure by way of a calculator. This is totally fine. Divided by, whoops, no, 3. And see that the other one is, as you knew, 49. And then it does get easier. 49, I see, oh, okay, it's 7 times 7. Both of those are, of course, prime numbers. And usually we pick numbers that have prime building blocks that are small and familiar numbers. So I can write this in any form I want. I like the exponential form. 2 times 3 times 7 squared. When it's 2 to the power of 1, we usually don't write the 1, but you're welcome to write the 1. So usually there is a smallish prime factor that makes the split fairly easy. In rare situations, it might not happen. So if you can't find a small one, you suspect this is an end of your branch, you want to circle it, then you have to be sure that it is a prime number. So it does happen, but usually we try and get ones that have small numbers involved. So 294 is built on or built with a 2, a 3, and 2 sevens, and nothing else. So the idea here is, as we'll see soon, that if I want to understand 294, I can do that by understanding 2, 3, and 7. And whatever properties 2, 3, and 7 have, 294, its properties will be very closely related to that. So the examples that we're going to do later will use these numbers and their prime factorization. Let's keep those two and do the other two on a new page. Like so. So we have 3. Number 3 is 702. So just whatever split I can think of, maybe you just want to use the 2. Maybe I want my tree to be a little bit more balanced. If I pick numbers of similar size, the tree will look a little bit balanced, but it doesn't matter, right? Here I could have said it's 2 times 50 for 100. 2 is an end node, we call it. Then 50 is 2 times 25, and 25 is 5 times 5. So my tree might look different, but I still get 2 2's and 2 5's. It doesn't matter what the tree looks like. It's going to result in the same prime factorization. Your tree might look different than someone else's, but the answer is not. And if you shuffle the 2's and the 5's, it doesn't change the answer. So I'm not too concerned with which split I want to use, as long as it's correct. But maybe I see, oh, it's divisible by 9, just to keep things a little bit more interesting. I might want to see, well, what is the other factor then? 702 divided by 9. It is 78. And you can always test, is 9 times 78 702? If it is, then your split was correct. So 9 is not quite done. It's a 3 and a 3, of course, finishing that side. 78, maybe I only see a 3, and then I'll just show something in the chat to confirm the 3 is a factor of that. 78 divided by 3, and I have 26 left. 3 is done. 26 is almost done. It's 2 times 13, and now both of those are done. And your tree might not look like this. It doesn't matter. In the end, when I sort of sort it nicely in increasing order, I get a 2, I get 3 3s, and I get a 13. Regardless of the tree, that collection of prime numbers are used to build 207. So we have a unique prime factorization, though many trees might get me there. Okay, so that's the first step. Use a factor tree, and of course a quiz question. These are fairly predictable, what the questions will be. It was only part 1 that had some variety. Variety is over. Use a factor tree to find the prime factorization of a given number. So you have to know what a factor tree is, how to use it, and then be able to write your prime factorization. The factor tree is not the prime factorization. It allows you to see the prime factors involved, but you have to write the prime factorization, which is a product of the prime numbers. Many people just do the factor tree and then stop. My question's done. No, it's not. You use that then to write your answer. You haven't technically finished. And because I've now said this, if anyone stops at the factor tree and doesn't write their product of prime numbers, I'm going to have to subtract something, unfortunately. We have one more, 240. So there, it is going to be a touch faster if I balance my tree. It's not important at all. But just to mix things up, maybe I see the obvious 10 times 24. 10 is a 2 and a 5. 24, there are many ways to go here. 4 and 6 maybe. I can't circle those. They're not prime numbers. 4 splits into a 2 and a 2. 6 is a 2 and a 3. And there, every branch is finished in that tree. I have 2 to the power of 4, 3, and 5. That is the answer. Though you get marks for the tree because the question will say use the factor tree to find the prime factorization. But those two things are technically not the same because someone else could have done trial and error and find the prime factorization. The factor tree is just a nice visual way and a thing that you may be teaching. Students do use the factor tree because it doesn't get much easier than that, and you can focus on little bits at a time and eventually find all the prime numbers. Okay, so we have these 4 numbers that we'll use in upcoming examples. I don't want to go too fast here because we have apparently 2 days scheduled for this, and the amount of material is not worth 2 days, but we don't want to get ahead of our schedule. But that just leaves some question and answer time at the end. If we finish today, then tomorrow, I guess, becomes a Q&A session. But we'll see how far we get. It doesn't have to be like that. The second part of tomorrow, at the very least, will be okay. So now we have 2 things that we want to do want to focus on, want to discuss. I'm just looking for my next example here. Here's the next example. Wow. Oh, it's at the bottom here. There we go here. Oh, it's very fitting. So move this up a little. Read it at the bottom here. Example 11.1. You have 24 pieces of Halloween candy and 30 pieces of regular candy to divide equally among some children. What is the largest number of children you can accommodate if both types of candy are to be divided equally? Though I don't know the difference between Halloween candy and regular candy. I thought all candy is Halloween candy, but whatever. You have 24 pieces of one type, 30 pieces of another type, and you want to split them up so that everyone gets the same number of pieces. Okay, so if I sort of go the basic way of analyzing this, I have 24 pieces of Halloween candy. I can give it all to one child, make their day, why not? I can split it among two children, and everyone would get the same. I can split it among three, four, but not five, because five doesn't divide into 24. Six children would work, not seven. Eight would work, not 10, 11, 12. And of course, I can split it among 24 kids. Everyone would get one. So I have a factor list here. List of all factors of 24. Those are the possible number of kids that I could accommodate. But at the same time, I also have to do this for my 30 candy. So for 30, I can accommodate 1, 2, 3, not 4, but 5, 6, not 7, 8, 9, 10. I can accommodate 15 by giving each one 2. And of course, 30 is as far as I can go. So now the question is, I'm looking for the largest number of children. So I'm looking for the largest number in this list that is common to both, and it's a 6. So if I want to split up my Halloween candy and my regular candy in this way, 6 kids is the best I can do. So we call 6 the greatest common factor, for obvious reasons, of 24 and 30. It's a factor of both. It's common to both lists, and it's the biggest one I have. So sort of work backwards. It's a factor, it's common, and it's the biggest, greatest common factor. And for short, because that's a lot of words and letters to write, we write GCF, and then we need to know what were the original numbers, because that determined my factor list and really decides everything. So GCF, greatest common factor, and in brackets, the 2 original numbers. Now you could do it for more than 2 numbers, but there's no real benefit in doing that. Okay, so GCF, greatest common factor. Now, that's perfectly fine at an early elementary school level because my numbers aren't going to be big, and little Timmy can hopefully make a list that is a reasonable size, and it doesn't take him too long to make this list. And once you have the list, great. You just see what's common and how far can I go? What's the biggest one? And you find the 6. Great. But that's a very basic way of doing it, a first step only, because once these numbers get bigger, then my list of factors will get bigger and bigger and bigger. And writing them all out isn't very efficient anymore. It would work if I want to spend the time, but I don't want to anymore. once this number gets big. And there's a lot of different factors. It's not just prime factors I'm listing here. I'm listing all factors. So we have to be a little bit more sophisticated, a little bit fancier when the numbers get bigger. Now I'll stick to these numbers because we have an answer for them and we can see in what other way can I get this answer of 6? Well, if I look at a number and want to know how it behaves, instead I can look at what its prime factors are, what its building blocks, and that will essentially tell me how this number behaves. And I can do that for both. So what we can do instead, as an alternative, in preparation for when this list making is inefficient, we can say, well, 24, I want its prime factorization. Well, I'm going to need a factor tree for that. 4 and 6 is one option, ending in 2 and 2 on the 4 side, and 2 and 3 on the 3 side. It's not a big number, so the tree isn't big either. But 24 is built with 3 2s and a 3. On the other hand, 30, I can maybe go 10 and 3. 10, oops, 3 is done. 10 is a 2 and a 5. So 30 rather is built from a 2, a 3, and a 5. So now if I understand what, oops, no, not a D, that's something else. Well, another situation, sometimes called GCD, greatest common divisor, though it hasn't really been used as much recently in my experience than greatest common factor. But I mean, these factors, divisors, technically a factor is a number that divides in without a remainder, whereas a divisor can technically be anything, whether there's a remainder or not. So greatest common factor is a little bit better as a name. But there was a time when greatest common divisor, greatest common factor, they were used interchangeably. Okay, so now if I just understand what these letters mean, I can use the building blocks instead of the numbers themselves to build the answer here. Okay, so now stop me if you don't like this, especially when we get to bigger examples. I'm looking for a factor. I'm going to go right to left here. I'm looking for a factor of 24 and 30, which means I can't go and use a 7, for example, because a 7 doesn't even feature in 24 or 30. It'll never be a factor. Any number that's made up out of prime numbers that do not feature in both cannot be in this, cannot be an answer. So if I'm looking at contenders 2, 3, and 5, those are the only prime numbers that I see. 5 will never be allowed to be in this answer because I need to have a factor of both. It has to be common. So though this 30 is built out of 5s, so 5 could be a factor in here. 24 does not like 5s at all. There is no room for a 5 in here, only 2s and 3s. So 5s are out, but 2s and 3s are in. So let me erase that. So I have to start with the prime factors that I see that are common to both, because the divisibility concept is sort of a fitting in concept. This answer needs to divide into both. This answer needs to fit in to both. And now I look at 24. 24 says, yeah, I'm happy with 2s and 3s. As long as you don't exceed 3 2s, you can fit in. And at the same time, I only have room for 1 3. So as long as you don't exceed that, you'll fit in and be happy. 30 says, I do like 2s and 3s, but I only have room for one of each. So even though 23 is happy with more, if you're trying to fit more in, I don't have room. I have room for 1, 2, and that's it. So the 30 and the 24 only allows 1, 3. So that's pretty much settled that. But even though 24 is happy with more 2's, 30 says, no, 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 only 1, can't do more. So I have to, unfortunately, limit my answer that I'm building here with just 1, 2. And that's how we get our 6. Now, once we repeat this a few times, it's going to get better. Don't worry about it. We now want to practice this GCF, greatest common factor. I want to make the biggest one possible, right? The greatest. So I want to use as many prime pieces as I can. But if I'm restricted by 1, then that limits me, unfortunately. All right, so now exercise 11.1, where we're going to use, no, not 11.1 at all. I'm looking at the wrong example. We're going to use the numbers we had previously and find the greatest common factor for some of those. Exercise 11.2. So we're looking for, actually I'm going to leave a space. Leave a space, and then we're looking for the greatest common factor of 100 and 240. So now I have to go and find where is 100. It was 2 squared, 5 squared. Okay, no, 2 squared. What is wrong with me today? Why am I in a hurry? We have so much time. I need to relax. 100 is 2 squared times 5 squared. 240. Where was that? Over here. 2 to the power of 4, 3, and 5. 2 to the power of 4, 3, and 5. So it doesn't matter that they come from the factor tree. I just need to see their building blocks, and those are the numbers in question here. So now I have to build a factor of each. So it needs to fit into 100, and it needs to fit into 240. Not at the same time, just the requirement comes in 2 parts, which means my answer here has to consist of the building blocks that I see. It needs to fit into both. So it's going to consist of some 2's and some 5's, not 3, because it's not common. Though 240 has some 3's in it, 100 says, no, I'm not linked to 3's at all. I'm not interested. I have no room for them. It's not what I'm about. So I have to start with the prime factors that are common to both. Otherwise, my number won't fit into both. Common. And I'm only using the building blocks that I see because they have to be factors. If I use other prime numbers, they'll simply not fit in the numbers that I'm interested in, because those numbers are made of 2's, 5's, and 3's. Now I just want to make the biggest one possible. So I want to use as many 2's as I can, as many 5's as I can, under the restriction that I have to fit into these numbers. So the largest number of 2's that I can have in my answer is 2. 100 can accommodate up to 2 2's. 240 can accommodate up to 4 2's. I need to be able to fit into both, so the best I can do is 2. 100 says, I'm happy with 2 5's. 240 says, no, I only have space for 1. So for that reason, I have to stop at 1, because I have to accommodate both numbers, trying to make it as big as possible, but I'm sort of stuck a little bit. I like to sort of talk my way through this, build this answer in this way, It shows a much deeper, much better understanding of what makes these numbers tick and what am I trying to do. Then you understand what's happening here. Instead of sort of blindly following a formula, use these prime numbers, and if this is bigger than this, and use this, and blah. No, it shows no understanding. I don't want to take a formula approach here. I want to sort of tell the story of how do I make this number. Now, I'm happy if you stop there. I like to see the prime factorization answer, but of course you can calculate it if you want. In this case, it's not big, it's 20. I don't care about the 20. That doesn't show me anything. The detail of the number by way of its prime building blocks, that shows me more. So if you want to calculate it, go ahead, but I don't want to see the 20 and not the detail. 20 is optional, detail is not. Let's see the detail. All right. Let's squeeze in the next one, then we can finish. The next one is GCF of 702 and 294. So I want to see what is behind 702. 702. 2, 3 cubed, and a 13. 2, 3 cubed, and a 13. And 294, regardless of where it comes from, maybe it was given, maybe you had to do the factor tree, regardless, 237 squared. All right, now I have it. So now I want to build my greatest common factor. Okay, let's do it. Sorry, I missed the YouTube question here. I don't know how long ago it was. I still don't know how to get the videos on Discord, so I can only type. That's okay. I see. Okay, good. Typing is totally fine. I just missed it. I didn't have the window open. Bad teacher. Okay, so I'm trying to build this. So a 2 is a common prime factor, and I'll worry about how many later. I can certainly use 3's in my build because they're common. And anything that has a 3 has a chance of fitting in. But I can't use 13 because 294 is not happy with 13. So it won't fit into both. 7 will fit potentially into 294, but not into 702. So that's as far as I can unfortunately go. Now, with the prime numbers that I have in my answer, I want to have as many of them as possible. 702 says, I only have room for 1, 2, sorry. 294 says the same thing. So 1 is unfortunately as far as we're going to be able to go with the 2's. 702 says, yeah, you can have up to 3 2's. I'm going to be fine if you have that. But 294 says, no, only 1. Only 1. So that's unfortunately limiting me as well. So that's my answer. That is 6 is the greatest, the largest number that can divide into both 702 and 294. I might feel that, no, surely there's a bigger number. No, there isn't. That is the biggest number that can fit into both. All right, are there any questions at this time? Now remember, you can write your answer as 6, but I always want to see the detail to help verify that you know how the prime factorizations are used to construct and build that GCF answer. Now, this is as far as the previous section got, and to stay in sync with them, we'll leave the next bit for tomorrow, but we can take the remaining time for today, as well as the second half of tomorrow, for just open Q&A session. So please let me know if you have any questions, but that is as far as we're gonna go today with the new material. So I'll hang around as usual in the Q&A sessions. Let me know if you have a question, Otherwise, we will talk tomorrow. Thank you.